Welcome. In this video, we will build an intuitive picture of surface rupture processes and their geomorphic implications. We will also see how scientists document them in the field and with modern technology. When a large, shallow earthquake breaks all the way to the surface, the ground is offset along the fault trace. That linear break at the ground is called surface rupture. Here is the key idea. The ground on one side of the fault moves relative to the other. In plan view, we often see a sharp trace, and in cross-section we can see a scarp or a step. Strike-slip faults mostly move sideways. On the surface, they laterally offset features. Imagine a fence or a stream suddenly shifted by a few meters. We may also see an echelon fissures and low-pressure ridges in the rupture zone. Dip-slip faults move up or down. A normal fault drops one side, and a thrust fault lifts the hanging wall. At the surface, we see a scarp, a vertical step. The 2008 Wenchuan earthquake produced a long thrust scarp with up to about 9 meters of vertical uplift and roughly 5 meters of horizontal slip. Surface rupture can disrupt drainage. A scarp across a hillside can dam streams, pond water, and divert channels. Strike-slip offsets can misalign stream courses. After the Wenchuan quake, dams and landslides created dozens of so-called quake lakes upstream. Rupture can be concentrated in a narrow band or distributed across multiple strands. Some earthquakes, like the 2016 Kaikoura event in New Zealand, broke many faults in sequence, producing an intricate pattern of scarps and tears, plus abrupt coastal uplift and nearby subsidence. Surface rupture can trigger cascading ground failures. Scarp cuts weaken steep slopes, causing landslides and rockfalls. Rupture can tap the water table to produce springs and sand boils. In water-saturated ground near rivers or coasts, lateral spreads can pull blocks apart. How do we document a surface rupture? In the field, geologists map the fault trace and measure offsets. Trenching across a scarp reveals layers disrupted by past ruptures, including colluvial wedges that record multiple earthquakes. Modern tools amplify our view. High-resolution LiDAR scans the ground before and after an earthquake, so we can subtract digital elevation models to quantify uplift and erosion. Drones map inaccessible scarps with centimeter detail. GNSS stations record sudden steps in position. INSAR reveals broad warping by measuring changes in the radar phase from space. By integrating field measurements with LiDAR, UAV, GNSS, and in SAR, scientists infer how much each fault segment slipped at depth. Complex earthquakes often involve several segments with different amounts of motion. Over thousands of years, repeated ruptures build the geomorphic record. Cumulative scarps grow taller, thrusts uplift terraces, strike-slip faults carve linear valleys, and offset streams. These landforms are the footprints of earthquakes through time. To summarize, surface rupture offsets the ground along the fault trace, with strike-slip lateral offsets and dip-slip scarps. It disrupts drainage, triggers slope failures, and alters elevation. We document ruptures with field mapping and trenching, and we quantify change with LiDAR, UAV, GNSS, and in SAR. Together, these observations link sudden earthquakes to the long-term shaping of landscapes. Thanks for learning with us. Stay curious